In Chapter 8, we looked at a sequence of terms, which is just a list of numbers with order to them. In Chapter 9, we're going to look at series of terms, which is the sum of a sequence. And we're going to try to tell whether an infinite series of numbers converges to a single number or whether that sum diverges. Today we're going to look at two different tests. One test will show whether an infinite series diverges, and the other test will show what to do with a geometric series. An infinite series, this is a definition, is if you take that sequence of terms and you add them all together. I'd like you to notice that an infinite series, if it converges, the answer is a number because it's the sum of all of those terms. This definition is how we actually add a series together. And the way we do it is we first add the first term, then we add the first two terms, then we add the first three terms, and we look at those partial sums and we notice that they form a sequence. We know how to tell whether a sequence has a limit, and it turns out that if that sequence of partial sums converges to a limit, then the series has that same sum. If the sequence of partial sums diverges, then the series diverges as well. Okay, here's the first example. What I'd like you to do is pause the video and take a look at that sequence of partial sums and see if you can tell whether this series converges to a single number or whether it diverges. All right. If I look at these terms, I'm adding one and subtracting one, adding one and subtracting one. It seems like my answer might be 0 because I'm subtracting as much as I'm adding. And in fact, if we grouped these terms, if we were allowed to group these terms, we'd be adding 0 each time. But order of operations says that we need to add our terms from left to right, and that matters. So what we're going to do is we're going to look at that sequence of partial sums, and the first term is 1 because that's the first term in our series. The second term in the sequence of partial sums is 1 minus 1, which is 0. The next term is 0 plus another 1, which is 1. And the terms keep alternating between 0 and 1. And since the terms of this sequence are not converging, our series also diverges. Look at this next example and see if you can do that same process to figure out whether this series diverges or converges, and see if you can figure out what it converges to if it converges. So pause the video and look at the sequence of partial sums so you can tell whether this series converges or diverges. Okay. If I look at that series sequence, the first term in the sequence is 3/10, which I'm going to write as a decimal. I'm going to write it as 0.3. The next term is 3/10 plus 3/100, which I'm going to write as 0.3 plus 0.03, which is 0.33. And the next term is 0.33 plus 3/1000, which is 0.003. So that next term is 0.333. And maybe you can tell that as I go towards infinity, this is approaching 0.3 repeating. And 0.3 repeating is another name for 1/3. So this series actually does converge to a single number. This series converges and has a sum of 1/3. Looking at example 1 and example 2 again, the terms in example 1 are not getting smaller and smaller, they're alternating. The terms in example 2 are getting smaller and smaller and smaller, so I'm adding teenier and smaller amounts to my sum. And it turns out that that's the nth term test for convergence. That in order for your series to converge, your terms have to be approaching 0. So your final term, your limit of the sequence has to be 0, or there's no way for your series, your sum of those terms, to converge. Notice that what this is not saying. This is not saying that if the limit of your sequence of terms is 0, then your series definitely converges. It's just saying that if your terms are not getting smaller and smaller and approaching 0, then there's no way that your sum can converge. In this chapter, you're going to have 7 tests for convergence. I would recommend that you keep them all together on a single sheet of paper. So I'm going to give you a chance to write this down. Please pause the video so that you can write this first test down. This is called the nth term test. So take a minute and write that. And when you're ready to restart, we'll do example 3. Okay, here's the third example. So visually what this example is saying is I'm going to take a whole object and I'm going to cut it in half. And then I'm going to take what remains and cut that in half and add it on. And then I'll take what remains and add that extra half on. And then I'll take what remains and add that half on. And if I keep doing that, visually, you can see that I'm going to eventually wind up with something really close to 1. If I do that infinitely many times, it's going to be 1. So that's the visual reason. If I look at that sequence of partial sums again, the first sum would be 1/2 because that's the first term. The second sum, and this time I'm not going to change to decimals, this time I'm going to find a common denominator, would be 1/2 plus 1/4, which is 3/4. And the next term, I'm going to add an eighth on, so I'm going to change 3/4 to 6/8 plus 1/8. So the next one would be 7/8. The next term, I'm going to add a 16th on, so I'm going to change that to 14/16 plus another 16th, which is 15/16. And maybe you can see that I'm getting really, really close to 1 as my numbers get bigger and bigger. By the time I'm to 1/28, I'll have 1/27 of them. So I'm approaching 1 as I add on these terms. So that's not a proof, but it maybe is pretty convincing. Here's the proof. This is your next convergence test, so this should go on that piece of paper. This is the geometric series convergence test. If you notice that example that we just did, it was a geometric series because each term was multiplied by the constant ratio of 1/2. So this is the definition of a geometric series. There's a starting term, and then each term after that is multiplied by your ratio. If you take the sum of all of those terms, it converges to a single sum, which is, I'll even tell you what that sum is. It's this, as long as it's a divided by 1 minus r, as long as your ratio, the absolute value of your ratio, is less than 1. The series diverges if the absolute value of your ratio is greater than or equal to 1. And some vocabulary. Since r has to be between -1 and 1, that's called the radius of convergence for the series. Okay. So that's the geometric series convergence test. It only works for geometric series, but it's pretty powerful. If you have a geometric series, you can not only tell me whether it converges or diverges, but you can tell me what the sum is if it converges. So, given that test, here's our next example. Take a minute, see if you can tell from this example what your A is, and if you can tell what your R is in this example. So pause the video and then come back when you have it. When I did this, I noticed that my first term is 2, and then after that I have 2 plus, so my first term is 2. My next term is really 2 times 3/5. And my next term is 2 times 9/25, which is 3/5 squared. So it looks like my R is 3/5. Since my R is 3/5, and since 3/5 is less than 1, this series converges. The series converges to, so we know that it converges, to A over 1 minus R. So we just have to plug in our numbers. So it's 2 over 1 minus 3/5. And then because of the way fractions work, this would be 2/5. We'd take 2 times 5/2 because we're dividing by a fraction. So it converges to 5. So the sum of all of these terms is 5, which is kind of cool. We're adding infinitely many terms together, and it just adds up to that small number 5. Last example, I'll give you a chance to figure out what A and R are so that you can tell whether this series converges or not. All right. So this series starts at pi over 2, and then each term after that is multiplied by pi over 2. Since pi is 3.14, pi over 2 is greater than 1, which means that this series diverges. Again, all you have to look at when you have a geometric series is you have to look at whether your ratio is bigger than 1 or not, the absolute value of your ratio. So here's a summary. The series is a sum of a bunch of terms. If the terms don't converge to 0, then there's no way for your series to converge. Your series diverges. And if your series is geometric, you're going to look at the ratio to tell whether it converges or not. If the ratio is less than 1, or the absolute value of the ratio is less than 1, then you know that your series converges to A divided by 1 minus R. All right, so that's a summary of 9.1a.